All right, hello everybody. We're going to start with chapter 4. We're going to talk about now organic chemistry is the study of compounds that contain carbon, no matter where they come from. Now, because of carbon's ability to form four bonds, these building blocks can be used to make a huge variety of organic molecules. So it's the fact that organic molecules contain carbon and carbon can bond to four things, makes carbon able to form all of these very diverse structures. So carbon, let's talk about carbon again. Remember the electron configuration of any atom, right? Or the atoms within elements determines the type of bond and the number of bond an atom will form with other atoms. So remember, molecules with multiple carbons, each of these carbons are going to be bonded to each other and to really three other things, right? So carbon can bond to four things. However, if you have carbon bonded to itself, or another one, not itself, it's going to be bonded to three other things. And when carbon bonds to these four things in total, it has that tetrahedral shape. So this shows that shape right here. Now, looking at carbon and some of the skeletons carbon can form, we see methane. Methane is just CH4, right? So it's just carbon with four hydrogens attached to it, and you can see that tetrahedral shape. Now, if you put two carbons together, we have ethane, right? So look what happens. We have the tetrahedral shape. They look like they're tilted on their side. And since this right here is a single bond, since that's a single bond, it's able to freely rotate around. So both of these sides right here, the CH3s, can rotate around the that bond. Right. Now, when you put a double bond, so remember I said that organic compounds can form double bonds. Remember, double bonds are two pairs of electrons being shared. So here we have a double bond. This creates a rigid planar format. And this is rigid, meaning that these two sides cannot freely rotate like they can with the single bonds. This is ethene. Now I'm going to kind of direct your attention to the names here. So we have methane right here, ANE. We have ethane, ANE, and then we have ethene. Look at ethane and ethene. Ethane and ethene both have two carbons as their base skeleton. However, ethene has double bonds, right? Whenever there's a double bond in a compound, often the suffix is ene. All right, so in terms of the diversity and arising from the variation of carbon skeletons, the carbon chains, as the carbons are being connected, it creates a chain, and they form skeletons. Now, the chains can vary in a number of ways. It can vary in length and shape, the presence or absence of double bonds, the location of those double bonds, and some have the ability to form ring-like structures. So we're going to take a look at some examples of these. Okay, so if we take a look at this, we have two structures of carbon compounds, one of them having two carbons and one of them having three carbons, none of them having double bonds. These are just differences in length, right? So basically, carbon can keep on adding to many, many carbons. In fact, there's a lot of fatty acids that have a long carbon chain that can be up to 20, up in the 20s in terms of numbers of carbons. Now, I just want to kind of point out some names here again, of course. So we saw this one already, ethane, right? There's no double bonds in there, so it's going to be A-N-E. And then we have propane. Vary in terms of branching. So look, these both have the same molecular formula. So basically they have the same number of carbons, same number of hydrogens, but the shape and function is completely different. So they could have the same molecular formula, but be completely different molecules, right? So here we have butane. This is 4 carbons in a straight chain with no double bonds, A and E. Now this one is 2-methylpropane. Remember propane from the previous slide, 3 carbons in a row? Well, this one's got a methyl on carbon number 2. So you can number these 1, 2, and 3, right? So on carbon number 2, there is a CH3. That's a methyl group. Remember that functional group. So I could circle that and call that a methyl. My handwriting is horrible with this thing. There we go. That should help. Sorry about that. This is commonly called isobutane, right? So look, we've got butane with 4 carbons. It's kind of a form of butane, but it's an isoform of butane. So it's just a different isomer. Let's look at double bond position. Right, so here we have butene. Remember butane, right? So butane had 4 carbons in a row. Now we've got butene, right? Butene, since it ends in ene, it must have a double bond. So in this case, the double bond is between carbon number 1 and carbon number 2. So it's called 1-butene. Now we have 2-butene. Well, the double bond starts at carbon number 2 and ends at carbon number 3. Right, so now we have 2-butene. Remember, it's got a double bond. Okay, so they could have varying positions of the double bonds, which can increase the number of different carbon skeletons or molecules that can be made just from a chain of 4 carbons and a bunch of hydrogens to fill the outermost shell. So we could have, basically, if you wanted to do 3-butene, right? So 3-butene would have a double bond right here, and then this one wouldn't have a double bond. So some of them can also have rings. And there's a couple different ways in which things can be shown. So it's important. This is where I'm going to kind of mention this. So we have cyclohexane. Hex meaning, right? So there's 6 carbons and there's no double bonds, A and E. And it's in a cyclic format. Right, so we can see here, we've got 6 carbons connected together, and this is the skeleton right here. And then, of course, enough hydrogens attached to each of the carbons in order to obey that octet rule and fill that outermost shell. Now, another way of showing this is this right here. So you might see this structure right here. These are equal, okay? So these corners are assumed to be carbons. Right, so whenever it doesn't show the atom, you should know that these are carbons. And it's assumed that each carbon has 2 hydrogens attached to them. Now here we have benzene. This is ENE. So this has got three double bonds, okay? And they're alternating. And these double bonds can move from one side to another. So they can move around. So that they can move like this, and like this. There's never going to be 2 next to each other. Okay, so you cannot have, so I'm going to go ahead and just draw this right here. You cannot have 2 right adjacent to one another. Okay, that does not happen. Okay, so we have a ring. And again, we've got 6 carbons connected together as the base skeleton. And then since each carbon has at least 1 double bond, so look, if you look at this carbon right here, it's got 1, 2, 3 bonds. Well, it needs 1 more, so it needs the hydrogen there. So again, here, this is assumed to be carbons right here, carbons. Okay, and it's assumed that each carbon has a hydrogen attached to it because there's 3 bonds within the ring, but then there needs to be another bond. Remember, it bonds to 4 things once it's happy. terms of structure. Now, I mentioned, I think, hydrocarbons before. So hydrocarbons are basically organic molecules consisting of only carbon and hydrogen. Now, some of them have an attachment at the end of the hydrocarbon. So here, this is an example of a fat. Okay, so you've heard of triglycerides, right? So you know some triglycerides or an overabundance of triglycerides can be very unhealthy for you, but they are absolutely needed for energy, right? So we do need some of these triglycerides. This is a triglyceride right here. So this shows the space filling model of a triglyceride. And what a triglyceride is it's, we're going to talk about this more when we get to chapter 5. Well, it's one base molecule right here which does have oxygen in it. Okay, so there are some oxygens. Okay, but attached to each of the carbons in this base molecule are long hydrocarbons. So this is a hydrocarbon right here. Okay, and there's 3 of them. Okay, so hydrocarbons are molecules that consist of only carbon and hydrogen. Now, isomers, and I kind of talked about this before, remember the isobutane. The isomers are basically compounds that have the same molecular formula but a different structure. And of course, along with a different structure, right, that means different properties as well. So we're going to look at some examples of isomers. Now, some of these you might be somewhat familiar with, and some of them are going to show in terms of branching and different types of shapes that the carbons can form. All right, so these are called structural isomers, right? So this is pentane right here. So this has got 5 carbons. Penta means 5. Pentane means that there are no double bonds in it. This doesn't have double bonds either. This is called 2-methylbutane. So I think we saw 2-methylpropane. Well, now we have butane. Look, we've got the 4 carbons in a row. This is the main structure, so this is how you would number them. And then on carbon number 2, it's got a methyl group. Okay, so we've got a methyl group on carbon number 2. These have different structures, but the same molecular formula. So basically, they have the same number of carbons, same number of hydrogens, but they have a different structure. Cis-trans isomers have covalent bonds, and they have covalent bonds that are going to differ in terms of their arrangement around a double bond. Okay, so you can see what's common here. The only way you can have a cis-trans isomer is if there is a double bond, okay, in the skeleton. So this just shows a skeleton with only 2 carbons. Here, remember when we were talking about the double bonds, this creates this planar structure, so it's very rigid. Okay, so I'm going to go ahead and draw this. And this is kind of flat planar structure. So you're going to have some atoms that are attached to the carbons above the plane of the ring. Okay, and some are going to be below the plane of the ring. Okay, same here, above and below. Okay, and I'm talking about the plane of the bond. I said ring earlier, sorry, I didn't mean ring. Now, above the plane of the bond and below the plane of the bond. Now we have 2, the X could be just any atom. So if we made this OH, let's say both of them are OH or hydroxyl groups, then both hydroxyl groups are above the plane of the ring. This is a cis isomer. If you have one, let's say, again, this is a OH, OH. Okay, well, here we have one above the plane of the ring and one adjacent or on the opposite corner below the plane of the ring. This is a trans isomer. Okay, so cis-trans isomers are going to be having certain bonds of things in terms of the arrangement across a double bond. Enantiomers are mirror images of each other. So if you put your hands together, right? So your thumbs were matching and all your fingers were matching. It's like they're looking at each other in a mirror, right? Same thing with molecules. This can happen as well. So both of these right here are the same amino acid. So we've got the C, and this is another way of writing this is COOH. And what the structure looks like is this. Okay, and this is the R group right here. This is what it's attached to. Okay, this is, remember, the functional group, it's a carboxyl. Okay, so there's a couple different ways of showing it. COOH, right? So I could write it out like this, CO2H and then COOH, and then this is the actual structure, what it looks like. And then, of course, all amino acids have also the methyl or the amino group. All right, so look, the amino groups are facing each other. The carboxyl groups are going to be going upward. The hydrogens are going out, okay, away from each other. So that would be like the thumbs in these hands right here. And then the methyl group is like the wrist, right? So amino acids have what's called an L isomer and a D isomer. Now, isomers, these types of isomers are very important. We're going to talk about this in terms of the pharmacological sense. So in terms of pharmaceuticals, the isomers matter. So some of them are going to be functional, some of them are not going to be functional. All right, so those are three main groups of isomers. So we have structural isomers, we have cis-trans isomers, and we have enantiomers. Now let's talk about the structure-functional relationship since we're on that topic. Your textbook discusses a few different pharmaceuticals regarding the enantiomers or the mirror images of these molecules. A couple examples are in this table right here. We have ibuprofen and albuterol. Ibuprofen is, both of these are relatively common. Ibuprofen is often used to relieve pain and inflammation, like Motrin and Advil. And albuterol is used to open up the airways to help asthma patients breathe when they're having an attack. Now, each of these drugs, or many other drugs, during the process of synthesizing them or creating them in the organic lab, different isomers may come up. And what they do during the process is try to set the conditions so that one isomer is in the majority of your product once the chemical reactions have concluded. Now, for ibuprofen, an S form and an R form, and also albuterol, an R form and an S form are formed. And these are mirror images of each other. They basically have what's called opposite chirality. So they're chiral molecules, however, they move in opposite directions. So only one of them is effective in the body. So only one of them is capable of doing the job that it was meant for, right? So ibuprofen, it's the S form, and albuterol, it's the R form. Now this kind of signifies how important the shape and the orientation of the atoms. So there are certain properties for organic molecules that really depend on the carbon skeleton and the chemical groups that are attached to it. Now, in terms of their chemical groups, right? So they could have different chemical groups or functional groups and have a different function, but having the same base skeleton. So two examples are this. We have estradiol and testosterone. These are two steroid hormones. So when we get to chapter 5, we're going to learn that steroids are a type of lipid, and lipids are typically hydrophobic, but many lipids have this structure right here, right? So the steroids have this 4 ring structures, right? So we've got 1, 2, 3, 4, 1, 2, 3, 4. One of them is a 5-membered carbon ring. The other 3 are 6 members. Some of them have double bonds with them. Now, both of these steroid hormones are general hormones, but they do have different functions, right? So what's common amongst them is that both of them have a methyl group. So this is methyl. Okay, this is a hydroxyl group. Okay, and then testosterone has a methyl group in the same spot and a hydroxyl group as well. What's different about them are two other things, right? So testosterone has an extra methyl group here. This is a methyl. Okay, and it has a ketone here. So remember, these are carbons. Okay, so we've got carbons adjacent to a carbon double bonded to an oxygen. That's a ketone. Okay, that's one of the carbonyls. All right, so, and estradiol has another hydroxyl group. So hydroxyl. Okay, so they have different functional groups attached to the same base skeleton, giving them a different function. It's the functional groups and different combinations of the functional groups that provide the properties of each molecule. Right, so this is really just a summary. I introduced organic chemistry, organic compounds, Stanley Miller's experiments, the properties of carbon. We kind of do a little reminder of that with electron distribution and how many bonds it can form in its tetrahedral shape. And also the variation in terms of carbon-containing molecules in terms of the skeleton, right? So they can have, and isomers, right? So that kind of goes along with the variation. So carbon-containing molecules can have different lengths and sizes. They could have double bonds and the number of double bonds, the position of the double bonds. Some of them can form a ring. And then the isomers, you can have structural isomers. You can have cis-trans isomers, and then enantiomers, which are mirror images of each other. All right, so we're going to start moving into macromolecules now in Chapter 5. Thank you for listening.